Hi, I'm Chris Brown, and this is lecture 2.13a in axiomatic design of manufacturing processes. This is the section on manufacturing processes, and here we're talking about surface metrology, in particular principles and basics. So the objective is to look at some of the basics on surface metrology, some of the shortcomings of traditional surface metrology, in particular average roughness, RA, and the other height parameters, and look at how do we go beyond this. Now, RA is actually, and all of the surface characterization parameters are essentially kinds of DPs that are used to describe the physical space. And some other characterization parameters can do a better job at telling surfaces apart, and importantly in the context of this course, for correlating roughness with performance and with processing. So this enables product design and process design. And I have something of a new science in surface metrology that we'll talk about as well. So surface metrology is the measurement and the analysis of surface topographies. Now, surface manufacture and performance. The surface manufacturer influences the surface roughness, and the surface roughness influences the performance. So measurement of the surface and trying to correlate it or differentiate different kinds of manufacturing processes or correlate with or differentiate different levels of performance, this is the job of surface metrology. So we call this discrimination, being able to tell surfaces apart, and functional correlations, correlating with performance or manufacture. Now, at sufficiently fine scales, the surfaces tend to be chaotic, and so this makes this kind of analysis particularly challenging. So the surface metrology system consists of a surface or a replica that needs to be measured. So the measurement consists of heights, usually on a grid in X and Y, and then some way of characterizing this, because usually these grids in X and Y are quite large. Typically, modern measurement devices will measure about 1024 by 1024, about 1,000 by 1,000 heights. And so this gives you a collection of over 1 million heights on a regular grid. And so this needs to be somehow analyzed. So the applications, of course, are for design, quality assurance, and then many different kinds of science benefit from measurement of surfaces. One that we've been involved with is physical anthropology and archaeology, or a couple that we've been involved with. All right, so discrimination and correlation tests. So this is what we're looking for and what provides the value. But there is other value in surface metrology, and the standards that we work on, and I am on both ASME B46 and ISO TC 213. These standards are essentially to promote commerce, so that a buyer and seller can agree that a surface has been delivered as requested. But what we would like to do would really be able to assure quality, and so be able to discriminate the surfaces that are valuable from the ones that are scrap. And, as I said, support product and process design. So these three things have got some value, and we're going to concentrate essentially on the second two. Promoting commerce is already fairly well covered by this, but often we're not getting good discrimination or able to find these correlations. So the thought is that they really require three things. And we'll develop this in the course of this lecture and the second one on surface metrology, and get back into this as well, I think in machined surfaces. But all right, so the characterizations of the appropriate geometrical aspect of the surface. This is one of the things you need to do. Might be heights. More often, perhaps slopes, areas, curvatures, for example. Now, all of these slopes, areas, and curvatures change with scale, and heights can too in a special way, and we'll show that in the next lecture. But characterizations at the appropriate scale. So area changes with scale, for example. As we look more closely at a surface, we see ups and downs, we see hills and valleys that we didn't notice when we were further away. So there's an old joke about Vermont would be as big as Texas if you could flatten it out. The Vermonters are quite proud of their hills. Vermont can't get as big as Texas. Texas has got a 20-to-1 advantage in just projected or nominal area, and you'd need quite steep hills. But people in Vermont are proud of their hills. All right, topographic measurements have to contain the appropriate scales and the appropriate fidelity to make these work. So the first two might be some sort of axioms or principles, and the next one, the third one, might be corollary. Anyway, these three things need to come together in order to do good discrimination and correlation. So why is surface roughness important? Well, so surfaces cover everything. Manufacturing is often about making the surface with the desired properties, sort of where you want it. And every manufacturing process influences the surface roughness, or virtually everyone. And roughness influences the performance. So here's a list, and this is not intended to be collectively exhaustive, but it shows many different areas or applications, performances that are influenced by the surface: scattering, heat exchange, mass exchange, flow resistance, nucleation, boiling, ignition, adhesion, wetting, cleanability. All right, so what do these relationships look like? Well, sometimes they're simple, and perhaps better roughness is better performance, at least over some range. If we're trying to, say, promote friction on stairs or sidewalk or a roadway. So rougher is better within some range that we're looking at. And so we can say, well, here's a performance tolerance and there's a roughness tolerance. And so we're going from an FR, here, performance, to a DP in roughness. And there's the relationship. Now, sometimes it's the other way. The smoother, the better. If we want something particularly shiny, for example. How smooth can you make it? So again, here's the FR for performance, and here is the FR for roughness. There's a performance tolerance, and try to translate this into a roughness tolerance. Sometimes it's even more complicated than this, and so in this case we have a situation which you have, say, with ski bases or hard drives, that the friction coefficient will go up as it gets smoother because a different friction mechanism is activated, something like capillary adhesion, which is favored by smoothness. All right, so processes that influence surface topographies, basically every manufacturing process that you can think of, and then some that are meant just for, like tumbling or mass finishing, that are meant just for changing the surface finish, brush finishing, for example. But on these other ones, the surface finish is maybe just a consequence of what's happening. So what do we mean by this term roughness? Well, engineering usage, if somebody just says roughness and gives you a number, they're talking about average roughness. But often it's just meant to mean small or small scale geometry. And often it's based on the instrument that we use to measure it. For the common usage, often people talk about something rough, meaning it's irregular. The Rocky Mountains are rough, they're irregular. So not smooth. And so we would need to look at some way of defining smoothness, perhaps related to entropy, but that's subject for a different lecture. All right, so filtering of geometrical components. At large scales, we have the form. For example, if we're dealing with a ball bearing, at large scale, it's spherical. Intermediate scale is waviness, and the finest scale is roughness. So, and waviness can often be thought of as just an intermediate geometry between form and roughness, although in the case of bearings, the waviness has an impact on vibrations. So here's an example. There's a measured surface, and so this is going to be equal to the form. So here's just the form part of this. Here is the waviness, and there's the roughness. So this is a milled cylindrical surface that is decomposed into three components: form, waviness, and roughness. So this is done because if I am evaluating, say, a cylindrical surface, I don't want the cylindricity necessarily to influence the roughness results, because there are things that interact with the surface at these finer scales, and I would like to isolate those for just the roughness. So there are cutoff wavelengths for the filters that provide roughness, waviness, and form. And it's kind of an open question. How do we know if we've selected the right ones? So in the ASME, American Society of Mechanical Engineers, B46.1, which is the roughness standard for the United States, and has been influential worldwide historically. So here are the different sort of filtering cutoffs for could be for profiles. So lambda C is the long wavelength cutoff for roughness. So here, if we look at a spectrum from very fine scale, high spatial frequency, small wavelengths, to large scale, large spatial frequency, long wavelengths, or small spatial frequency, long wavelengths. So here is the upper limit of roughness is lambda C. The short limit of roughness is lambda S. It's thought that the very finest scales are noisy in this kind of decomposition. Lambda CW is the long wavelength cutoff for waviness, so this tells us where form starts, and lambda SW is the short cutoff for waviness, and this tells us what the lower range of waviness is, and this may be the same as the long wavelength cutoff for roughness. So here's a representation in the spatial frequency domain with the highest spatial frequencies or smallest wavelengths denoting the roughness. All right, conventional texture characterization parameters. So if we represent, say, a profile by a series of dots here with a height z along some n number of dots along an axis x. Now note that characterization parameters that begin with S refer to surfaces where we have z, the height, measured as a function of x and y, and R profile is z, the height, just measured as a function of x. So what we're actually looking at here is just a profile. Now the peak to valley, or RT, and could be ST for a surface, is from the lowest valley to the highest peak. The arithmetic average roughness is the sum of the absolute value of all the heights. And we use the absolute value because if we didn't and we had the mean line in the right place, added it all up, should come to 0. So that's simple arithmetic average of the absolute value. Or we can use root mean square, which is also the same as the standard deviation, because we've subtracted the mean by using this line. And so we do the square root of the sum of the squares over n. Now, the problem with averages is that in the average, one big peak can be the same as two little peaks, can be the same as two little valleys. Now, these surfaces might have very different performances. This one would be good for oil and debris retention, for example, and these would both be kind of tending to scar the counterface in a sliding kind of situation, or might be providing good friction in another kind. So RA, average roughness, most is the most used, and so if there is no qualifying information, the RA has its part right here on the symbol, historically, and so we may just see RA by itself. Now, the RZ is an average of the maximum heights in a certain number of sections. So this is going to be a little bit, say, more robust than just the peak to valley height, which might be influenced by some kind of outlier, where this will tend to be less influenced by single values. Now, those were height parameters. This is a spatial parameter. So how far is it between profile irregularities? And so we have an average spacing like this. But in order to do that, we need to define, so where's a height? Where are we going to cut this profile to define what an irregularity is? And does this count as one, or two irregularities? So the peak count has got a similar problem. We need an upper boundary layer, and then we say before we can count another peak, it's going to go below the lower boundary. So here is a trace on a machine surface. We can see these cusps. We'll be taking a closer look at machine surfaces in another lecture. And so we have this series of cusps, and we see that there's, so it looks like there's different frequencies involved, spatial frequencies. So we can take out the waviness, and so sort of the roughness is removed, and now we're just looking at the waviness. Now this was along a cylinder, so there's no real need to remove form since it's nominally straight. So here we're looking at the roughness with the waviness removed, and so we can see how different this is and how much more regular this is once we've taken out that component. So if we add this one to this one, we'll get this one in here. Now we have to be careful with the cutoff because the filtering has different sort of cutoff lengths, and this can dramatically change the height parameters. So if we take a rather short cutoff here, which is approaching the feed, the regularity in this, we can see that the RA is very much smaller than it is with, say, a longer cutoff. As a matter of fact, the difference is 41%. So without changing the profile at all, just by changing the cutoff filter, you can dramatically change. These are all different height parameters. We looked at RZ and RT. RP is the peak height. These all get changed by a large amount with different kinds of filtering. So we can show this too in a sine wave, and we can calculate RT, peak to valley, RA, the average roughness, and RQ, root mean square. So we can do this in a certain amplitude. We can calculate and figure out what it is, and if you remember from calculus, this would be 1 over the square root of 2. All right. So what happens if we take something with a smaller amplitude and higher spatial frequency? All right, we can calculate that too, and here it is. And we can see, yeah, everything's a lot smaller on this blue line than on the red line. That's kind of what we expected. Now the next question is, what happens when I add the two lines together and then calculate the parameters? So the really interesting thing is the RA, the average roughness. The purple line here that goes up and down, little ups and downs and big ups and downs, has exactly the same RA for the red and the purple. Now this higher spatial frequency superimposed can obviously have some impact on this and on the behavior. It might be scattering light or sound or something, or influencing adhesion or cleanability. So the surface with all the ups and downs can have distinctly different behaviors than the large-scale smooth surface. But these differences, will not be discoverable by the average roughness. So what are the trends? So we have to be careful of RA for a couple different reasons. So what are the trends in surface metrology? Well, one is to go to multi-scale analyses. I'll take a look at those later. And another is to go to more functionally based parameters. So some multi-scale characterizations, and these are kind of scale-based decompositions. So we have height, and that's fairly monoscale. But then we can take the first derivative, and that can be the slope. Now the slope is going to change with scale. At large scales, we tend not to see any slope, and if we look at the very fine scales, we can see more ups and downs. And note that the height parameters lack any spatial information. So until we take the spatial derivative, there's no spatial information. Now, if we go from slope, the second spatial derivative is curvature, approximately. And there's a couple other ways of calculating the curvature. So what we're looking at here in these kinds of decomposition is spatial derivatives. Now, we're not taking a derivative because we're not going to try to fit an equation to this that we can take a derivative of. What we're doing is we're looking at the slope as it changes with scale, or the curvature as it changes with scale. And, excuse me. So we use finite approximations. All right. The scale derivatives on the last one was kind of an error. So some of the things we look at here are that we've developed at WPI: length scale, area scale, and filling scale. And if we take the scale derivatives of these, we come up with things we call the complexities that we'll run into. And there's a question mark here because we haven't actually taken the filling scale that far yet. So then we have spatial integration as we go from length to area to sort of volume-based or filling. Thank you very much for your attention.